Now, in our triple integrals, we are now starting triple integrals, and this takes the form. You have three integral signs. Then we are integrating within a solid of integration, where this Q stands from the solid of integration. That is where we are going to get our limits for Z, for Y, and for X. So the limits, because we have got three integral signs, one depending on the arrangement of our dv here, the limits will be indicated either, if you start with x, that is you have dx, dy, dz, you put limits for x in terms of y and z. Then you come to dy, you put in terms of z. And when you come to dz, now we put the limits in terms of constants. Actually, a triple integral is always also a definite integral. Now, when you start with z, dz, you put the limits for z as a function of x and y. When you come to the next integral that you're evaluating, now, when you have dy here, you put now the limits for y in terms as a function of x. And finally, you clear with x, which will be in terms of constant. So depending on the arrangement or depending on the order of integration, then that's what will give you limits from the solid of integration that you're trying to use. So we can have an example to illustrate this, how it is being done. And before we do that, we say, we note something small. If you want to get the volume of a solid, you say, a function of x, y, and z is equals to 1, then the integral, the triple integral dv, if here we have 1, will be equal to volume of solid Q. Volume of solid Q. Equal to volume of solid Q. That will be equal to volume of solid Q. So we can have an example. So in example 1, you are given such a triple integral to evaluate. When you are given such a triple integral to evaluate, we are going to have this in our solution. It says 0 to 3, 3 to 4, 1 to 3, 5y plus 6x z squared dz, dy, dx. This will be equal to 0 to 3, 3 to 4. So we are integrating this function with respect to z. That is, we are keeping both x and y constant. So this will give us 5yz plus 2xz cubed. 2xz cubed. And then we input our limits 1 to 3. Then we are yet to integrate with respect to y and with respect to x before we finish. So this will be equal to 0 to 3, 3 to 4. When we insert limits for z, you're going to get 15y plus 54x plus 54x minus 5y minus 2x. Then we still remain with the dy, dx. This one simplifies to the integral from 0 to 3, the integral from 3 to 4. Then we have 10y plus 52x. We do with respect to y, and then x, dy dx. So this one simplifies to we are now integrating with respect to y. When we integrate with respect to y, we'll have from 0 to 3, then when we integrate 10y, you get 5y squared. We integrate 52x, we get 52xy. And then we input limits from 2 to 4. Then we remain with the dx. Inserting limits for y, 0 to 3. We're inserting limits for y. So 16, 80. We have 80 there. We are inserting for y. Plus 208x minus 20y minus 1 over x dx. So let's have an example. So evaluate this triple integral where q is the solid bounded by the surface z is equal to 4 minus x squared minus y squared, and z is equal to 0. So this is a solid bounded by two surfaces. So because the two surfaces brings out clearly the values of z, and from the indication as we are seeing, we can see this one is above this one. So this will be the lower limit for z, and this will be the upper limit for z when we start with dz, dy, dx. So this will be upper limit, this will indicate lower limit. Now, the last two integrals will be obtained from the region of intersection. So we need to know where our two surfaces intersect. It brings what region? So we say in our solution, the region of intersection is obtained when z1 is equal to z2. That is 4 minus x squared minus y squared is equals to 0. This implies what? X squared plus y squared is equals to 4. So the region of intersection is a circle. The region of intersection is a circle. Radius 2, center 0, 0. So this implies our triple integral, okay, here, x squared plus y squared dv will be equal to a triple integral x squared So we have x squared plus y squared dz dy dx. Now we are integrating this. The z value, lower limit for z is 0. Upper limit for z here, we have said it is this surface, which is equal to 4 minus x squared minus y squared. That's the upper limit for z. Now, our region of intersection is a circle. Now, from this limit, and it is a full circle, y will be changing from negative root of 4 minus x squared to positive root of 4 minus x squared. And the x values will be changing from minus 2 to positive 2. Minus 2 to positive 2. Because it is a circle, remember, of radius 2. So this one will be equal to the integral from minus 2 to 2, the integral from negative root of 4 minus x squared to positive 4 minus x squared. Now, when we integrate with respect to z, we get x squared plus y squared because they are being kept constant, multiplying z. We put limit 0 to 4 minus x squared minus y squared. And then we have here dy dx. We have there dy dx. This should be equal to the integral from minus 2 to 2 from minus 4 minus root of 4 minus x squared to positive root of 4 minus x squared. When we insert these limits for z, we get x squared plus y squared multiplying 4 minus x squared minus y squared. The lower limit, when you multiply, it will give you a 0. So we end there for that insertion of limits. Now, because we know these last two integrals, these limits came from a circle. And the circle is a polar region. So we can now convert everything into polar coordinates. We can now convert everything into polar coordinates, which will give us now the limits from that circle. It's a circle of radius 2, so r will be changing from 0 to 2. And theta will be changing from 0 to 2 pi. X squared plus y squared in polar, that is just r squared. Now multiplying 4 minus r squared, because x squared plus y squared is r squared. Dy dx will be r dr d theta. R dr d theta. So when we evaluate this one further, we get 0 to 2 pi. We are integrating 4 times r squared times r, which is 4r cubed, which gives us r power 4. 4r cubed, we get r power 4. Next we have here this r squared times this times, that is r power 5. So we'll be having r power 6 all over 6. Then we input limit 0 to 2, and then we remain with the d theta. We remain with the d theta. So this one will be equal to 0 to 2 pi. When we insert those limits, we get now 16 minus 64 all over 6. Then we have here d theta, because the lower limit will bring a 0. So this one, when we integrate, we'll get 32 all over 6 theta. Then we put limits from 0 to 2 pi. When we insert this 2 pi here, it will be 64 all over 6 pi, which is the same as 32 all over 3 pi. And that is the evaluation. That is the evaluation for that particular triple integral over the said solid. So use triple integral to determine the volume of the solid bounded by the planes. X is equals to 2, x is equal to 1, y is equal to 3, y is equal to minus 2, z is equal to 0, and the surface z is equal to 5 plus x squared plus y squared. Now, whatever we have now is a solid bounded by all those planes. So these 5 are straight planes, and this is the only curved surface. And this curved surface, when you check from z limits, this one is above this other one, which has got a which has got the variable z. So this one will be upper limit for z, this will be lower limit for z. And since these are just constants, we will get our limits easily here. So we simply say in our solution, volume is given by triple integral. Limits come from the solid, then we put dv, which will be the same as triple integral. Now, still put this, and let's start with the dz, dy, dx. Let's start integrating with respect to x, followed with y, and then z. This one will be equal to, this one will be equal to triple integral, starting from z equal to 0 to z is equal to 5 plus x squared plus y squared. Then the values for y starts from minus 2 to 3. The values of x starts from minus 1 to 2. So we have here dz, dy, dx. Now, on evaluating this integral, we have this one will be equal to minus 1 to 2, from minus 2 to 3. And now we are integrating with respect to z, we get z, then we input limits, 0 to 5 plus x squared plus y squared, dy, dx. Which will be equal to, from minus 1 to 2, minus 2 to 3, when we insert this element, we get 5 plus x squared plus y squared. And then we have dy dx, which will be equal to, when we now integrate this with respect to, we integrate it with respect to y. Integrate it with respect to y, we'll be having 5 plus x squared multiplying y plus y cubed all over 3. And then we insert our limits from minus 2 to 3, then dx. Still remain with an integration with respect to x. So when we insert the limits for y, what do we get? The limits for y. This here will be 3 into 5 plus x squared plus plus 9 minus, when we put this, it's also minus, so plus 2 into 5 plus x squared. This one is a minus. With the minus of integration, it will still be a plus 8 all over 3. Minus 8, so plus 8 all over 3. So this is what we are integrating with respect to x, which will then give us from minus 1 to 2. This added to this, we get 5 into 5 plus x squared. 5 plus x squared plus 35 over 3. 35 over 3. 35 over 3. This is what we are integrating now with respect to x, which will then give us what? We are now integrating with respect to x. We are integrating with respect to x. So this is a scenario where we have the integral from minus 1 to 2. 5 times 5 is 25. 25. 25. 5 times 5 is 25. 110 all over 3 plus 5x squared. That's what we are now integrating with respect to x. So when we integrate this, we get 110 all over 3 x plus 5 all over 3 x cubed. We put limits from minus 1 to 2. Put limits from minus 1 to 2. Which simplifies to which simplifies to 20 all over 3 plus 40 all over 3 plus 40 all over 3 plus 5 all over 3 not 5 or 9 plus 110 all over 3, then plus 5 all over 3, which will be equal to, which is equal to 125. And this will call it, because it was a volume, we'll say 125 cubic units, because it was a volume. 125 cubic units. In the cylindrical coordinates, sometimes we use cylindrical coordinates. It helps us in evaluating triple integrals where the region of intersection, where we have the base region, is from a polar region. So by that time, we can always convert everything in terms of cylindrical coordinates, meaning we mix both polar and Cartesian. And that is what cylindrical coordinates entails. Now, if the coordinate of a point in Cartesian is in terms of x, y, z, then its cylindrical coordinate is in terms of r, theta, z. That is, in cylindrical coordinates, x is put in terms of r cos theta in polar form. Y is also put in polar form. And z will be equal to just z. We maintain the Cartesian way of writing z. So in our dv, it will be r dr d theta dz, which will be the same as r dz dr d theta. A ds is a small portion on the surface. And if it is a cylindrical surface, on the surface of a cylinder is like, now you have this pen. This cylindrical in nature. And when it is cylindrical in nature, in any case, you are just moving over this particular surface. The radius does not change, or the distance from the origin, according to the particular axis we are referring to, is not changing. Hence, r does not change. So the only things that are going to change as you move around, theta is bound to change, and as also you move upwards along, let's say, this cylinder, z is also bound to change. Hence now, a small portion of that surface will be represented as r dz d theta. That one helps us so much when we are dealing with surface integrals. When we want to analyze what happens over the surface, that's what we use. We use the ds, a small portion of the surface. Now with this now, we can have an example to show the conversion of the cylindrical of a coordinate of a point into cylindrical form. So example, determine the cylindrical coordinates. So determine the cylindrical coordinates of the point 3, 4, 7. Now x here is equals to 3. Y is equals to 4. Z is equals to 7. This implies what? This implies what? R will be given by x squared plus y squared square root, which will be equal to square root of 3 squared plus 4 squared, which will be equal to 5. Theta will be tan inverse of y all over x, which will give us tan inverse 4 all over 3, which is equals to 53.13 degrees. We have now z will just be equal to 7. And therefore, cylindrical coordinates or point P, cylindrical coordinate or point P is given by P is equals to 53.13 degrees, then 7. Now, an example to go to application of that, the cylindrical coordinates. Application of the cylindrical coordinates. So, in our example 2, we can say evaluate this. We can see the last two integral is a portion. It's a region which is a portion of a circle. And since now we are dealing with the triple integral, then now we can now mix everything and have it convert everything into cylindrical coordinates. That is because the last two integral signs represent this region represents a portion of a circle, which is a portion of a cylinder. Hence the conversion to cylindrical coordinates. If we would like to do our evaluation without a problem, which is not tedious, for example. So we are going to convert the whole integral into cylindrical coordinates. So in our solution, say 0 to 2, 0 to root of 4 minus x squared, 0 to 2 minus x squared minus y squared, x squared plus y squared raised to power 5 over 2 dz dy dx. This will be equal to a triple integral, whatever we have here is now r power 5. R power 5, because x squared plus y squared is r squared. R squared raised to power 5 over 2, you get r power 5. We have our dz dy dx now becomes r dz dr d theta. Now we are integrating from 0. This becomes 2. X squared plus y squared is known as r squared. So 0 to 2 minus r squared. Now this represents a first quadrant of a circle. First quadrant of a circle. When it is drawn, when it is just sketch it, this first quadrant of a circle. So we say r is changing from 0 to 2. This is a circle radius 2, center 0, 0. Now theta will be changing because it is just a quadrant. Theta will be changing from 0 to pi all over 2. 0 to pi all over 2. And that is now the integral that we can now be able to evaluate. So this one will be equal to 0 to pi all over 2. We are evaluating 0 to 2. Then when we evaluate, we get r power 6z. R power 6z Then we input limit 0 to 2 minus r squared. Then we have here dr, then d theta. This one will now simplify to 0 to pi all over 2. 0 to 2. When we insert this one here, we get 2r power 6. 2r power 6 minus r power 8. Then we have here dr, d theta. The lower limit will bring zeros. So when we integrate this further, we get 0 to pi all over 2. This will be 2 all over 7, r power 7, minus r power 9, all over 9. Then we input limit 0 to 2. Then we remain with the d theta, which will be equal to 0 to pi all over 2, 0 to pi all over 2. Insert this one here. When we insert 2 power 7, that is 128 times 2 to 56 all over 7 minus 512 all over 9. This is what we are integrating with respect to theta, which will give us 256 all over 7 minus 512 all over 9, the whole of this multiplying theta. Then we put from 0 to pi all over 2. When that one is inserted, when we insert those limits, so the answer is negative 640 all over 63 pi. And that's the evaluation to that particular integral.